Morning, friends. It is Ben again, and this is a video set up for to cover the material that we will be doing on Tuesday, April 25th in class. I am recording from home. I can't quite get the lighting set exactly right, but hopefully you'll be okay with that. All right. So the thing that we're really talking about is going to, for Tuesday, is going to be the notion of probability, especially normal probability. But we're going to try to look at some other distributions just very briefly as well. Okay. So the reason that we have to talk about this is that what we're doing with a lot of things in data science is trying to see whether our evidence is strong enough for something. Okay. And the way that scientists do this, now I'm going to give you the warning, I'm doing it a little more formally, probably, than a real scientist does it. Okay. But the way that a scientist does this is they check to see whether the data differs significantly from what simulated data would that didn't do what they're trying to prove. Okay. So whenever you're doing this, you are always looking at data that you think shows a difference from something. And you are saying, well, if it's not what I think, here's what would happen. And then we compare our data to that model, and we say, what's the probability we get the results we did if it weren't different? You know, what that comes down to is, what's the probability this data came about by random chance? Okay. So to understand what's going on with that, we need to talk a little bit about probability, a little bit about distributions, and I'm trying to get several weeks worth of the Math 112 class into just one simple lesson. So bear with me a little bit. We're going to try not to make it any more painful than necessary. Okay. So let me see whether I can write something real quick here on the screen. So I'm going to share screen, and I'm going to tell it that I'm going to do this with an iPad, tell it to share, and then it says it has to download a package before it can do that. So give this a second. Sorry, I should have anticipated that that was going to happen. Okay, now I'm going to go over to the iPad and mirror to the Zoom connection. And it is going to tell me, no, it does not want to mirror to the Zoom connection. So bear with me a second as I tell it instead. Yep, I know you weren't able to do that. I will tell it instead that I want to share screen to just my regular old desktop. And that will appear super junky, but then I should be able to tell it to take over that screen with my iPad. And then I sit patiently waiting in order to find out that no, it can't do that either. Okay. So we'll try another option that does not work very well at all. We will share a whiteboard. I have not tried writing on this before, so bear with as I tell it to write something, and the thing I'm going to write here is probability. Oh, that's great. I just totally wanted it to be light blue, which you can't see very well. And there is nothing I can do to change that. All right. So here is a notation that you see a lot in math and statistics, the probability of E. So it's a probability of some event. So the event means something that you can describe. And so you might have the probability that X is greater than 2. Okay. If I were able to draw, I would then put an X bar over a bar over the X, because that would mean the probability that the average of a bunch of data turns out to be more than 2. That is a typical event that we'll see on these things. Okay. But because I can't, I'm just writing probability X is greater than 2. You can just as easily have the probability that X is less than 3, or the probability that -1 is less than X is less than 2. Okay. So in all of these, we're going to be talking about some measurement that we're doing things with. And we would talk about getting the probability that they were bigger than something, less than something, between two things, something like that. Okay. Now, in all of these, we can totally have that it's equal to things. I just can't type that. And my iPad is not going to connect, so drilling. All right. I'm going to go ahead and tell it on this to stop the share. And we're going to jump over to something else, right? That I can kind of control better. But I need you to pay attention to what those we're talking about, that we would have these various things there, the probability of these different events. And yeah, and so that's what we're talking about today, is those probabilities, and then also the notion of some distributions. Okay. So the next bit that I'm going to try sharing here is going to be that guy there, right? So what you should be seeing on the screen there is a drawing of what we refer to as a normal distribution. I'm going to show you a better drawing here in a second, but because I was able to produce this in the notebook, and you'll see it as you go along there, this is a curve that has a formula for it, but you totally don't need to know the formula. It's complicated and has exponentials in it and stuff, but it's something you don't need to know. What you need to know is that the normal probability that you're looking at there is a curve that is symmetric. It's the same on both sides of this hump that's in the middle. If you've got a single hump, you say it's una, that means one. Modal. Modal means hump, I guess. But a normal distribution is unimodal, one hump, and it's symmetric. Okay. And it has other properties that are a little harder to actually talk about without some technical stuff. But we do a lot of things with the normal distribution because it turns out to appear everywhere. And the reason for that, you would need a good stat course in order to see the actual reason why it shows up everywhere. But we're going to do things with it and with some other distributions as well. I want to point out here that in the notebook that you'll be looking at, you come down here and I have things like the probability Z is between -1 and +2. Okay. Anytime somebody's talking about normal distributions and they start making reference to Z, Z is the standard normal, or maybe you could say standardized normal, but it's a normal distribution which has as its mean, the middle of it, of 0, and its standard deviation, which is just a measure of how spread out it is, but a standard deviation of 1. Okay, so standard normal is talking about that. Whereas if you just set a normal distribution, you can set it up to have any mean, and then you can make it spread out, or you can make it very skinny, either way. Okay. So I'm going to jump over here to a different app that I've got referred to as GeoGebra. You do not need to worry about downloading this, but if you're interested in doing more math stuff, it's a handy app. It works pretty much like Desmos does for plotting, but it has more stuff like this that I'm showing you now built into it. So normal distribution, generally speaking, is going to be something with a curve like that in the middle. We can take and change where the center is. I can tell it I want the center at 10, and then we would have to think about something a little bit different here. Maybe I'll go then that we want to fill in from 9 to 12. Okay, just as an example there, right? The total area under this curve is going to turn out to be 1. If you went all the way out forever to the left and right, you would get an area of 1. So probabilities are always going to be numbers between 0 and 1. You can never have a negative probability. You can never have a probability that's more than 1. Okay. If you get those numbers from a calculation, you did the calculation wrong. Okay. If you get a probability of 0, that means that the event you're trying to get the probability of is impossible. It will never happen. If you get a probability of 1, that means it's a certain event that it always happens. So if you talk about the probability of flipping a coin and having it come up heads, you know that that should be about 50%, so 0.5. If you talk about flipping a coin and getting Mississippi, no crap, I guess with those state coins you could get Mississippi to come up. Okay. If you talk about flipping a coin and getting it to come up with a blank side, okay. If you're talking about American coins that are in circulation, they don't circulate coins that have a blank side on them. So the probability of that would be 0, right? And if you talk about you have a 2-headed coin and you flip it, the probability of heads is going to be 1, right? So these probabilities of events follow that sort of thing about impossible, possible, and then certain. So here for this, when we talk about the normal distribution, you're getting a number that you're talking about the distribution of, and it's some number that has some randomness to it. Maybe you're talking about rolling dice. Maybe you're talking about going into the lab and taking a measurement in an experiment. Now, measurements and experiments should be predictable, but there will be some variation, and that variation is the random variable end of it. Okay. So when we talk about this sort of thing, normal probabilities often come up, and we often want to know things like, I've got this standard normal variable here maybe, and I want to know the probability that I get a number between -1 and 2. So from the picture, you can see that you've got a certain area there, and it's not the entire area under the curve. So that means that you're going to get a probability that's less than 1. And so this calculation here was getting it to be 0.81859. Okay, that's a fairly likely event. Okay. If you get a probability that's less than 0.05, we start thinking that's pretty unlikely. And when it's less than 0.01, we say that's very unlikely. Okay. But that's the sort of thing that we're doing on these is you will have some kind of a model going on where you believe that you've got a normal probability for the difference from the model. And then we're doing a calculation later that we'll talk about that probability of the difference from the model being very small means that surely there was something going on. You couldn't have had that model, that normal distribution model, and have gotten the data that you did get. Okay. So with regard to these probability distributions, I do want to point out, I'm not sure how well you can see this, but there's a place where it says normal distribution there. And I'm going ahead and taking and choosing a list. And I wanted to show you that there's some other distributions as well. One here that's referred to as the student's t distribution. If you blinked, you probably did not notice the change, right? Let me go back and forth here a little bit. If you look at a normal distribution and a t distribution, and then a normal distribution, and then a student's t distribution. So the student's t distribution is a little bit taller on the edges and a little bit lower in the middle. It is a special distribution that takes into account some things that you're often not able to calculate. And so it's just a convenience, something that we use when we can't calculate everything just right for a normal curve. We're going to have this chi-square distribution come up as well. The chi-square doesn't look like a normal distribution. It is stuff, it is lopsided, asymmetrical, and it has no numbers that are less than 0. And then it goes off here to the side, depending on this degrees of freedom setting that you have on it. It determines how quickly it dies off as it goes off to the end. Okay, so that's going to come up later, and the calculation that we often do with it has an infinity here, and maybe we have like I don't know, 12.5 there or something like that. Okay, and it tells me it cannot actually calculate that. That's weird. I didn't know it couldn't do that. All right. Well, let's then do this the other way on it. And I'm going to give it some definite ends that will start at 0 and we'll end it at 12.5. Come on. 12.5. Okay. So it gave me, if you see that there, a 0.9483, and that's the area to the left of it. Okay. So this thing of getting the area to the left of a certain number is referred to as calculating the CDF, cumulative distribution function. And when we go back to the normal distribution, if I'm not sure if we can do this or not, minus nth. Yeah, okay, it understood that. So the area that is to the left of +1 is 0.84134, okay? There's no way for you to calculate this stuff by hand. You have to go to the calculator or Python, okay? So we're going to take a look at using that CDF to calculate some things in the actual notebook that you're looking at today. So share screen again and go to Google Chrome. All right. So here we earlier were talking about the normal distribution, and then I will zoom in so that you can read this. And so from the Skippy stats package, you have a distribution called norm. I have not messed with them, but so I don't remember whether the student's t is going to be called t or if it's going to be called student's t or something. And the chi-square will almost certainly be called just chi-square. Okay, but we'll have to import those things in order to be able to calculate with them. And then this function here, where I say norm CDF of 2. So that would be the thing that we were illustrating earlier, of taking this normal curve, cutting it off at 2 and doing stuff to the left. I don't know how the mirroring is going to work on your computer, so I may have just put stuff to my right instead of left. But anyway, so it's getting the area to the left of something. So norm CDF02. So if you notice down here, when I executed, it came up to say that the area to the left of z equals 2 turned out to be 0.9772. Okay. And then if I wanted to get the area to the left of -1, that turns out to be 0.1586. So the Python doesn't seem to have built into it the thing that your calculator has built in, where you would say norm CDF -1 to 2 in just one step. But instead, if you want to get the probability of something being between -1 and 2, what you do is to calculate the probability of it being to the left of 2, to the left of -1, and you subtract. Always subtract big minus small. If you subtract and get small minus big, you'll get a negative number, and areas are never negative, and probabilities are never negative. Okay, so if you get a negative number, go back and just change your order. Likewise, though, sometimes you need to know the probability that z is greater than something. And the trick on that is to just take 1 minus. Since the whole area is 1, the probability of being to the right of 1 is going to be 1 minus the probability of being to the left. Okay, it's referred to as complementary events. So I'm going to ask you to do something here where you figure out how to do that calculation as well. All right. Then also, I didn't provide you code for this, but I want you to figure out how to do it. Well, I provided you the idea of the code. I didn't actually give you an example. But if you have a different mean or a different scale, sorry, what did I say? A different mean, which is mu, that's the middle of the distribution, or a different standard deviation, that's sigma, and it just determines how stretched out it is, then you can just go in and in your norm CDF statement, just tell it LOC equals and whatever that mean is. And different standard deviation, you can say scale equals and whatever that standard deviation is. Okay. This should be pretty easy, but you may have to experiment a little bit with how you type it. So I ask you to do that here. And then, yeah, and then going on down here, I went ahead and told it to generate some data. So you remember how we had the computer do that dice rolling stuff the other day? And that dice rolling stuff was a simulation. And we have something built in that will automatically do a simulation for us of a normal variable. So here, when I say x equals norm.rvs, the RVS means random variable sample, okay? And so it tells us, I told it to go get a sample that has a mean of 75, a standard deviation of 12, and a size of 20, okay? So to make that a little bit more concrete, that is basically what I tend to see on the average statistics class, that the average for an exam tends to be about 75%. The standard deviation tends to be about 12%. And I said size of 20 here, okay? So, but yeah. So then I went ahead and told it to take that and sort it so I could see it in order a little bit better. And I also asked it to get the mean of that, okay? Now notice here, it came from a population with a mean of 75, But when I random sampled, it just so happened that I got a sample with a mean that was a little bit less than that. It happens. Okay, don't worry about that happening too much, but it can happen. So insofar as these numbers, notice that they're all floating point numbers. They go out 8 places past the decimal. And for talking about scores that you would think about in classes, it seems a little silly to have decimals coming in them. And so I think in the next step, I show you how to go ahead and round them off. And I'm completely wrong about that. Okay, so what is this here? Turn to simulation and see if Python can give us a histogram. Okay. Is that? Huh. Okay. Simulation equals that. Simulation. Okay, so I told it to do that. And then size equals 20. And yeah, I'm just getting an idea of whether it looks right and such. So you ought to go ahead and do that sort of thing, see whether what you're generating looks right. But the important thing I'm going to do here is to actually generate a big sample and then tell it to make a histogram for it. Okay. So looking in here, I said my simulation is going to be a list, and I've got a sample size of 20 each time, and I'm going to append the mean of each of those lists into the simulation. Okay. And the reason that I'm doing that is here at the end, I'm going to, I just spotted a mistake that I made. I think I wanted to say to plot it, the histogram not of X, but of the simulation. Let's see whether that changes the thing I was getting. And it says, no, it can't possibly do this because I didn't import something. By the way, this is an important lesson for y'all. If you have something that you need to use and you might need to do it out of order, then you need to put the import statement in every cell. Okay. So let me try that again and see whether it does it better. Yeah. Okay. That looks better. I had a typo where I was plotting X instead of the simulation. So, and I was wondering why it was not looking the way I expected it to. So you take a look at that and it looks kind of like a normal distribution. It's fairly symmetric and it's unimodal and stuff. In fact, if I go up here and change my size for my sample to be 50 instead of 20, you'll see that it tends to get a little bit more like a normal distribution. But the thing we're working with had 20, so we'll be satisfied with that. So anyway, it looks kind of like a normal distribution, but as I mentioned here, let's see, histogram of simulation. Okay. Yeah, so yeah, it looks kind of like a normal distribution, but your mileage may vary on there. Okay. Yeah, I don't know. So then the thing that I mentioned here is you get those plots and they look okay, but they don't look great. In the original iteration of this, the plots I was getting just didn't look very good at all. Okay. The stuff we were getting weren't, oh my God, I misspelled the word symmetric. I feel so dumb. So, and then I can't even find it. All the plots that I got looked Okay, but not great. And I need to spell the word symmetric right. I've gotten used to a spell checker helping me out all the time. All right. So anyway, though, instead of doing things from looking and guessing, we have a little bit better method that's referred to as doing a normal probability plot, a norm plot. I've heard it called a lot, but apparently it's referred to as a QQ plot in Python. And so the thing that you do with that is that you take your data and you feed it to the QQ plot, and it plots out the data with, I forget whether it's the X or the Y axis. I think it's the X axis being theoretical standard normal distribution. And then the model that you've got, the actual data you've got, will be the Y axis stuff. Okay. So here's what happened when I did this. Was I doing it with X? I should try to do it with simulation and see if that helps. Simulation. Okay. And then the straight line that I put in there isn't really relevant. But okay, so if you do that with the simulation, the thing that you'll see is that that data looks to be a straight line, like really straight, except for at the ends of it. But if we do that with the X instead, his QQ plot only sort of looks like a straight line. And let me put my guess of a straight line back in there. And my guess isn't very good. Okay. So originally I had this set in there where it was doing a fairly good job of getting it drawn. Oh well. So in any case, though, when you do one of these QQ plots, then you look and see, does the data we've got look like it's a straight line? If it's a straight line that's kind of hooked a little bit at the ends, that's not too bad. But this one here, it looks like it's a little crooked in the middle. Okay. It should be pretty straight in the middle, but it can be off a bit on the ends. If it's pretty straight in the middle, then we say it's approximately normal, and then we just go on with our work. Okay. So a lot of what we're doing for stuff today is this kind of idea of getting something approximately normal and saying that we can then go on with our day. Okay. If you're doing work and you are using the standard packages that assume that you have something that's normal and it's not, then you are going to have faulty assumptions and you'll get conclusions that are just wrong. If you get conclusions that are just wrong, you get in trouble. Okay. So anyway, here's an example of something where they sampled a distribution that is clearly not normal. Okay. It's referred to as the log normal distribution. So it's related to the normal, but it's the logarithm of it. Okay. And as you'll see, the QQ plot that you do for that doesn't look like a straight line. There's a straight line there just for reference. And so we would, in that case, say, no, we have to go model this with a different distribution instead of the normal distribution. Okay. So I wanted to give you an example of something that did look normal and something that didn't look normal. But the thing that we're heading towards here is referred to as the central limit theorem. And the central limit theorem says that if you start with data that came from a normal distribution and you take the mean of a sample, if the original distribution was normal, no matter how small your sample is, you're going to get something that's normally distributed. If you start with something that's not from a normal distribution, if you take a large enough sample, the means that you get will turn into something normal. So here, for example, let's see, we go ahead and get our random variable to be with the size of n, n equals 30. And then I went ahead and did a relatively small sampling of it. But when the size of my sample was 30, even though I was taking from a log normal distribution, once I got the means there, I got something that's pretty much a straight line, okay? So it tends to be, if you're talking about means taken from a large, means taken with a large sample, you'll get a normal distribution no matter what. And some of our theory that happens later on will depend on that, okay? So the thing that I want you to do on this is to take that code, copy it down below, and experiment with changing the little n, okay? Experiment with changing the little n and see where it seems like we start to see a simulation come out where it's noticeably not a straight line, right? That's ill-defined. I didn't say what the criteria are for close enough and not close enough, but that's what I'm wanting you to start to get an idea of here, is that we have to make some judgment calls on stuff, and your judgment call here will be, when does it look close enough to a straight line? I'm going to say this does look close enough to a straight line, so try setting your little n values to be larger and smaller and see what it changes. Do that down here, okay? And then time permitting, I'd like you to do it again with some distribution other than the log normal. And I give you a link there to go visit to find the names of some of the other distributions. Okay. All right. And then I also go ahead and do this piece here, where I went ahead and got that data that we did the MPG miles per gallons from the other day. And we're going to pull the miles per gallon data from a specific model of car. I went through and I spotted that Kia was one of the models of cars, and that's what my wife drives. So I went ahead and pulled the data for Kia. This shows you how to do that. And then if you go ahead and do that graph again with the city miles per gallon versus engine displacement. And somebody made the point to me the other day, this is super weird. Kia apparently puts out a 5-cylinder car. No, 5-liter car. My wife's little Kia has a 1.8 liter engine. So it's down in this range here. But in any case, though, we're going to pull this data, and then we're going to throw the miles per gallon portion of the data to one of the QQ plots. And when we do that, we can see it really does not look normal at all, right? But this part here, to the left of about 1.5, looks fairly like a straight line. And so I kind of followed that across there and said, that looks like the cutoff somewhere around 30, okay? And so I did this thing of cutting out the piece of the data that had the city miles per gallon less than 30. And then I pulled the miles per gallon data for that again and redid the plot. And now it doesn't look like a perfect straight line, but it looks fairly straight, okay? what I'd like for y'all to do is to go ahead and do that with the highway mile per gallon. Okay. So whereas here we were talking about city 08, that one will be HWY 08. I haven't actually done it, but take a look and see, does the QQ plot on that look approximately normal? If it does, great. If it doesn't, see if you can cut down and see just a portion of the sample that does look fairly straight. Okay. Actually, I may have just lied to you. I think I actually did this, and I think for Kia it does turn out. Okay. But if you're interested in doing this, whereas I took here and pulled, what did I pull? I took and pulled the data that was not electric and that was Kia's, right? If you want to do Dodge or Alfa Romeo or anything like that, you can just change make to that. But do all the appropriate stuff for it down in the cell at the bottom, okay? Remember, if you didn't run the cells that I did stuff in, then things have not been loaded. You'll have to import things, and you'll want to import it from your own data set that you've got sitting on your hard drive. Okay. So anyway, I am going to go back on these and put numbers in there so that you can spot which ones, where the things are that I'm asking you to do stuff. But that's what I'm looking for you to do. Some normal probability stuff, and then some normal plotting to see whether something is approximately normal or not. Okay. Hopefully this is not too rough, and I'll see you in class.